So let's get started quickly. To help speed up things a little bit, I have written down some of the stuff that we will be discussing today. Okay, hold on. There we go. So we're going to talk about just a couple of topics from the first chapter in the book, and then we will move on to the second chapter today, and you will have your second quiz today as well, somewhere in between the set of topics that we are going to discuss. And so what I will use now is just the highlighter so that we can go through this. And some of you actually who have done the math physics class with me are already familiar with the first set of topic, which is the pseudo vectors and pseudo scalars. We will take a look at it in more mathematical detail this time, so that even if you have seen it before, you will get something new. And for those who haven't seen it, think about it after we have finished the discussion today. Read through the textbook, and then you will get some idea on why these concepts are important. And then we will talk about Helmholtz theorem, which is essentially what most of the electro and magnetostatics is based off of. And then we will start discussing electrostatics. Once we are done with electrostatics, maybe maybe a week from now, we will start looking at magnetostatics, and then we will come back to dielectric matter and then magnetic matter. So we're going to go back and forth between the electricity and magnetism discussions. Okay. So normally when you talk about vector, we talk about, at least in the entry level physics, you talk about vector as a quantity with magnitude and direction, which of course is not correct. And what you need instead is something called orthogonal transformations to describe how vectors transform when you change them from one coordinate system to the other coordinate system. So let's say I have a vector here, vector v. The same vector v is going to look exactly the same even if I end up choosing a slightly different coordinate system to express its components. Okay, so the vector doesn't change. It's because of the choice of the coordinate systems, the components change. And so there is quite often a need to transform the vector component from one coordinate system to the other coordinate system. And that is done through a so-called transformation matrix, which is essentially all possible dot products. You have three unit vectors in the EI, in the first coordinate system, and EI prime. Those are the three unit vectors in the second coordinate system. Because you have 3, you can make 9 possible combinations of their dot products, and those 9 combinations is what gives you the transformation matrix. The order is very important. So if I'm going from, so if I want to express a vector in the prime coordinate system and want to determine its normal EI coordinates, then the transformation matrix would look like this. So E1, E1 prime, E1, E2 prime, E1, E3 prime. So I missed prime there. And then same thing for E2 and then E3. I would like M to be the matrix that takes vector EI and transforms into EI prime. That's why I'm calling this one MT, right? So the transpose of the actual transformation matrix that I'm interested in. And so if you know how to write MT, you can write M as well, right? It's just change the order of the dot products, and then do the transformation. So the first column will have all the E1s, second column will have E2s, and third column will have E3s. That will take you from EI coordinate system to EI prime coordinate system. Okay, so make sure you pay attention to this this T here. Okay, it's crucial. You get the order wrong, you're going to get wrong signs sometimes. But the general property of the orthogonal matrices is M times M transpose is commutes with itself, so you can change the order, but the product always is an identity matrix. And in this case, the identity will be 3 by 3. Another property of the transformation matrices or the orthogonal matrices is that their determinant is always plus or minus 1, which you can kind of see from here. All of these are going to be cosines of the angles between the different vectors. And so the product, it turns out, would be just plus or minus 1. All of those combinations when you do determine the determinant. And so if you have a vector, you can write down the component relations of that vector in any coordinate system based on the transformation matrix. So Vi prime, just using our index notation, Vi prime would be Mij Vj, and the repeated index j is being summed over. Right? So that's important. Don't forget that. Everybody with me so far? Okay, nothing new. We're just trying to mathematically formalize what's happening here. And the goal now is to transform or see the transformation properties of things like the vector product, right? Or the cross product of vectors, right? So we're going to look at this. How does this transform? Okay. And so what we do is first do the look at one of the components, just like we do with the help of the Levi-Civita symbols. So the first component is Mi. Let's say the ith component is going to be Levi-Civita epsilon ijk pjwk. So you're all comfortable with this now. And once you have that, let's see what will happen if you were to express this vector in the EI prime coordinate system. It's going to be, let's say Mi prime would be its component in the ith direction in the prime coordinate system. And you can write that possibly as epsilon ijk, pj prime, wk prime. But the question is this really correct? Is that how it's going to transform? The cross product in one coordinate system is just the same as in the other coordinate systems. So any thoughts anybody has? Is this correct? You can tell me in the chat privately, yes or no. Let me see, I need to monitor the chat. I don't see any answers yet so far. Just privately a message to me only, not to everyone. And okay, keep the answers coming. I have only 2 answers so far, and you're at least 13 of you in the class. Okay, most of you are saying yes, and maybe 1 or 2 no's. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it looks like everybody has answered. So we're going to go with go with the majority. So this expression is correct. But what's troubling actually is, can I write, can I write mi prime as m I j m j? That is the more important question. Let me put a box around it. Okay, so these expressions are fine within the coordinate system because they're not trying to connect the two coordinate system. They are within their own coordinate system. A cross product is a cross product. If you would just take the components and write that down. Now, think about this one carefully. And again, some of you already know the answer because you took the class with me, mathematical physics, and the rest of you may or may not know the answer. So the question now is this correct? Okay, so that was our first question. Now the second question is this correct? And why? And again, and let me know your answers again in the chat. Okay, I'm beginning to get some answers. Okay, now these are not all the same. There is no majority opinion on this one. It looks like we have mixed feelings about this one. Okay, so let me take a survey of where we think now. 1, 2, 2. Okay, looks like the majority here is tending towards no. So we need to now, I won't give you the answer just yet. We will go through it in details and see what's going on here. Okay, that's our question 2. Okay, so I just clarified that those two questions are different, and so we don't get confused. Okay, so let's find the answer to this question 2, not just as yes or no or majority voting. Let's rigorously prove what or find out what the answer is using mathematics, right? So this we know, right? Using the transformation matrix, Pj prime is going to be MJSPS. Let's take another vector, the W. WK prime is going to be MKLWL. Remember, I'm using different indices so that we don't confuse them, right? And so with this, once we know the PJ prime and WJ prime, we have just agreed that this relation is correct. So if this is correct, we're just going to use it and start substituting the transformed or start substituting Pj prime and Wk prime in the original coordinate system, right? In terms of the components from the original coordinate system. So that's what you get here. You get epsilon I jk. That was just there to begin with. Then Pj is replaced by MJSP. Pj prime rather is replaced by MJSPS. And WK prime is replaced by MKLWL. Okay, everybody with me so far? Once you have that, then we are going to, we can exchange the order of the m's. We can bring them together because these are now just simple components, simple numbers, so they compute with themselves. So you can move them around. So move ps and wl at the very end. You need that for the cross product definition. So right here, you could sort of see there is something more to it than just, so compare this relation just to aid your thinking. If this was to be just the standard, I don't know the indices here. Let's figure out what indices we will need. We're looking for mi. So epsilon I, j, k, or because we have ps, let's just do epsilon I, s, l, pl, no, ps rather, ps, wl. If the transformation properties, like the question to number 2 answer, the answer to question number 2 was yes, then we would have m, let's see, I needs to survive, so I need mi, j, something needs to be repeated, so it's not quite clear. This is a vector with the I component, and then I needs to be summed over. So this needs to be, let's call it j, just to be sure. And so you would have mij epsilon j s l p s w l. That's compared with, right? You can already begin to see that that's not what it looks like. It looks like it's slightly more complicated than that, right? And so let's highlight this part. We want to, either we want to transform the yellow highlighted expression into this other expression, or we want to prove that they are not the same, right? Either we prove that they are the same or we prove that they are not the same. Okay, so that's the idea. So the question still remains. I haven't answered the question yet. Are they the same, right? So let's pose the question. Right. And so let's go through this. We see that the epsilon ijk now can be rewritten as epsilon njk delta in, right? Very simple because of the property of the two. And so we can, rest of it is just copied as it is, so nothing new here. Okay, I think I should not use that highlight just to avoid confusion. Okay, so rest of it stays as it is. Now let's recall the delta I. Now we're going to do some manipulation so that we can simplify this delta in term a little bit. So everybody okay with this, right? That's just the transformation properties. ei prime would be mij ej. The new set of vectors, unit vectors, ei prime and ej prime are orthogonal. So it's going to be delta ij. But I can write this as a dot product of the transformed dot product from the original coordinate system. And so the first term, the ei prime, I can transform it to look like mik ek prime, express it in terms of the original coordinate system. Do the same thing for ej prime, write it as mj theta e theta. And so you have now these two, dot product between these two terms, which are basically transformed from the original coordinate system. And you can then bring the m's together. So the mik and mj theta are together. And the rest of this stuff here is going to be the dot product, which is going to look like a delta function, delta k theta. So what we have proved is the expected answer for the dot product between ei prime and ej prime is delta ij. But with the help of this, I just proved, right? So you can take a look at, I will add a step here. You have basically MIK, MJ theta, delta K theta. What does that mean? If I have delta K theta, that means I can replace what? Anybody? Just unmute yourself and tell me what the answer would be there. Whenever you have delta K theta, remember Einstein summation convention, it's always there. Index K and theta, right, they have to be exactly the same value, right? So what we do is in the remaining expression, when we get rid of the delta, is we replace K with theta or theta with K, either one. And so I'm going to replace theta with K. And so you get MIK, MJK. That means what we have proved is that this delta IJ is this product here, MIK, MJK. Everybody with me? So what we have done is we have connected the components of the transformation matrices, provided you choose them in the right order, then they give you the delta function. Not the delta function, Kronecker delta, right? So Kronecker delta in terms of the MIK, MJK. So the K index is common. That means it's being summed over. So the final summation would not have any K remaining. So you will have just I and J would be the hanging indices, and that's what that is, right? So these are essentially relating the two tensors. Remember, delta IJ is a rank 2 tensor. So are MIJ. That's a rank 2 tensor as well. So now we have figured out, because MIJ is orthogonal, we are able to express it in terms of the delta IJs. Okay. So take that, let's take that and replace this delta IJ with this new formed product of M's, right? And so when you do that, you are going to have the epsilon NJK, that is as it is. The two deltas that we had are replaced with this. And because you have delta I and N, you will have to bring in one extra common index, which is Q, right? So that's a new index. And MIQ, MNQ would be equal to delta IN. Okay, that's where that comes from. And then the rest of the stuff is carried as it is. So nothing new there so far. Everybody with me so far? Right. So what we did was we started with the primed coordinate system expression for Mi prime, because it's a cross product with P prime and W prime. We wrote it as Levi-Civita and the P prime and S prime. The P primes and the W prime, they were expressed now with the help of the transformation properties in terms of the components PS and WL from the original coordinate system. We did simple manipulations, added the delta function, and then re-expressed that delta function in terms of the product of the two M tensors, right? To two transformation matrices. Okay, so what we do now is then now we combine the terms that I'm highlighting here with an arrow, right? So 4 different terms. Why? Because they have their first index common. Remember Levi-Civita, or remember Levi-Civita has 3 symbols, and then each of these selected M's have their first index common with the Levi-Civita symbol. And so because eventually you're going to do Einstein summation, all of these terms will get combined anyway. They're going to get reduced to something that carries only the indices Q, J, Q, S, and L. And so that's all that we have done here. Combine those highlighted terms, and the rest of the terms stay as it is. And now this part you can again compare with, right? So I'm going to highlight it with a star. MIQ, PSWL, we are kind of beginning to get into that form there. So it's getting closer, but not quite the same. There is just so much of the set of tensors in the beginning that we need to deal with. Okay, everybody with me so far? Any thoughts, questions, concerns? Okay, now we need to manipulate this part. And for that, you can recall some of the discussion from from section 1.4 in the book, where the determinant of a matrix, right? Some matrix C multiplied by epsilon LMN can be written down as Levi-Civita epsilon ijk CLI or IL, does not matter whether you do row major expansion or column major expansion. Either way, it's perfectly fine. And then you have CMJ and CNK. Now, of course, we haven't proved that, but it's something that you can prove easily with the help of the properties of the Levi-Civita and the fact that the determinant, which is the product of these three quantities itself, is a antisymmetric tensor, right? So that's what that is. So this combination is what we have here. So we have now an opportunity to simplify it. We don't need to carry all of those indices, the I is getting summed over. And so we're going to replace the epsilon njk, mnq, mjs, mkl by, so let's see what happens. The indices n would go away, j would go away, k would go away, and the remaining three indices will be left behind for the remaining Levi-Civita, and then you have determinant of m, right? And determinant of m we already saw is either plus or minus 1, depending on what sort of a transformation it is. But it's always going to be that because it's an orthogonal matrix. Okay, everybody with me so far? So this jumble of 4 terms has been now simplified into just one specific Levi-Civita with the right kind of symbols and the determinant of m. So now we get mi prime as the new term that we just figured out how it works times miq pswl. So you can already begin to see now you have the epsilon pswl. So that's like the cross product. M would transform it, but now you have this extra determinant of m cropping up there somehow, which is a little tricky, which makes it different from what you would expect normally, right? So let's take let's manipulate this a little bit more carefully so we see that difference. So let's pull out the determinant here. Let's put the transformation matrix miq, and then you have epsilon qsl pswl. This part that I have underlined here, let me put a box, a dashed box around it. Right, this dash box term, which I'm going to call star. I'll just put a star there, and we will compare it with what we were trying to look at earlier. You can see it compares quite nicely with this. Here I chose mij epsilon j sl pswl. It doesn't have to be. I and j are the indices that are arbitrary. So because the j is summed over, I can replace that with q like we did here. So if you replace j with q, this start expression and that start expression is exactly the same, right? So it is what we were expecting. It has that form, except for just one little thing, which is there's the determinant of m appearing in front. Except for that, mi prime is transforming correctly, right? So let's think about it again. This would be, right? This is m I q, then little m q, and you have mi prime equal to that. Right? That's what the expectation would have been, but we are what we are getting is not quite that. It has an extra determinant m in front. Everybody with me so far? So those were the expressions in the component form. We did a very detailed manipulation to arrive at this. Let's now write down the vector relation, which gives us that the m prime now is the m vector, the m transformation matrix applied to P cross W, but there is this extra determinant of m in front. That means there is plus or minus 1 sign. It does not always. If determinant of M is +1, then it's identical. Then the vector, the cross product vector is transforming properly like a normal vector. But if determinant of M is -1, then you don't get the expected direction for the cross product vector after transformation. Somehow it changes direction, and that's the weird part, right? So that means the cross product is not quite a vector in the standard sense. It's not transforming correctly, even though if you go back to your entry-level physics classes, you treat cross product as any other ordinary vector. But there is a little bit of a sophistication that needs to be added because it does not always transform as a vector would transform. There are cases in which there is an extra negative sign coming into the picture. Right. So let's recollect the expectation. V prime is equal to mv. So if p prime is mp and w prime is mw, it turns out that p prime crossed with w prime is not m times p crossed with w. So they're not equal, but it's not too terrible, right? They're more or less proportional to each other except for that one extra sign. And these kinds of quantities, p cross w, we cannot call them vector anymore because it's not transforming like a vector. It's not a strict equality. There is an extra sign coming in, which is coming from the determinant of m. We call them either pseudo vectors or axial vectors. And the ordinary vector is termed as a polar vector. Everybody with me so far? Okay, so not only you know now that vector themselves are the standard definition for the vector, which is magnitude and direction is not accurate. You need transformation properties. They need to transform correctly. And the cross product is not quite a vector. It doesn't transform properly. So let's make sure you understand the names, right? Pseudo vector or axial vector is the new type of vector that you have seen, and the standard vector that you're familiar with, we call them polar vectors. Okay, so let's take polar, axial, and we are going to use these two terms in the E&M class. Now I have some questions for you. Okay, and you can write in the chat what you think the answer would be. And the answer always is there are only two choices, axial or polar. Right, so let's take one question at a time and make sure you think about it carefully by taking care of the determinant m, which is just one or plus minus one. So it's actually very easy, even though we haven't thought about this, it's very easy to think about it. So take a minute and think about what will happen if you take an axial vector, which is a cross product to begin with, right? Axial vectors are the cross products type vectors, and take another cross product of that axial vector with a polar vector, which is an ordinary vector. What would you get? If you think about it and then send a private message to me, and we'll just take a vote on what the majority says. Okay, I only have 3 answers so far. And I have 6 answers now, I think, no, 5 answers. Okay, somebody answered all of them, 1, 2, 3. That's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 10. I have okay, Fatima, I didn't get your answer, but rest of you have answered. So yeah, I only see one. I don't see the actual answer. Okay, so I think that's plenty. I wasn't expecting answers for number 2 and number 3, but some of you actually gave. So that's good. That means you're thinking ahead. That's very nice. But let's figure this one out, right? So the actual vector, let's think about the transformation properties, right? Only when you think about the transformation properties are you going to get the nature of the vector. So the actual vector, when it transforms, rest of the transformation part stays the same. I get an extra factor of the determinant of M, okay, for actual vectors when you transform. The cross product will give me another factor of determinant M, and polar vector transforms just like itself, so it does not give me any factor of determinant. What is going to be determinant M squared? That is going to be 1. So as if that determinant M was not there, that means this is going to transform like an ordinary vector, so it's going to be a polar vector. So if you answered polar, you got it. If you answered axial, you were not thinking along the correct lines. So everybody with me so far? Does that make sense? Just nod. I can actually see you. Those of you who have your videos on, I can see you, so you can let me know visually. Okay, does that make sense? So this is how you want to check. Now let's take a look at this one. Polar vector, no factor of determinant. The cross here would have a factor of determinant M, and this other polar vector would not have any factor of the determinant. So you have only one determinant left, which is like a actual vector. It will transform like an actual vector. So it's actually nice, thankful that only one factor of the determinant matters. If you get 2, or if you get even powers of determinant M, then it's like an ordinary vector. If it's an odd power then of determinant M, then you get a actual vector. So that's all there is to it. Thankfully, there are only just 2 kinds, and they're very easy to figure out. So let's take a look at this one.
Kapale, can you repeat number? Can you repeat number 1?
Number 1, okay. So actual vector, if you transform that, it's going to give you an extra factor of determinant M. You agree? Look at the transformation property of an actual vector, right? So let's write it down here. Actual vector in the prime coordinate system is determinant M times the transformation matrix times the actual vector. That's my notation, okay, actual vector in the actual coordinates, right? So you have this extra factor of determinant M that you have to carry, okay? Plus, whenever you add a cross product, you have a, we just saw for P cross W, whenever you transform a cross product, you get that factor of determinant also. So in the first case, you get, you get the determinant M from the actual vector, another factor of determinant M from the cross product, because it's the cross product that changes the vector character from 2 ordinary vectors to the polar vector, or, as we are seeing, if you have an ordinary vector times an actual vector, a cross product, it leads to a polar vector, right? So in some sense, those 2 determinants cancel each other. Same thing here. Polar crossed with polar vectors transforms as themselves, so there is no changes there. You basically have, like we saw in the previous case, right? Like the example that we went through, That was a case of polar vector transform, cross product with polar vector, which gave us that extra factor of determinant M. So you can ascribe determinant M with every cross product, right? So it's just appearing once. So we're going to end up with the actual vector. Let's take a look at this one now. What is going to happen here? You have three properties or three quantities that will transform, and we have to determine whether they will have their own determinant M or not. So actual vector will have its determinant M term. The cross product will have its determinant M term. It's the cross product that changes the character of the vector. And the another actual vector that will have a determinant M. So you get the determinant M to the power 3, which is an odd power. And so you will be left with the actual vector. Or we call it pseudo vector. That's another name for it. Does that make sense? Everybody with me? Now,
Yes.
I have another question for you. What if we had something like this? In ordinary vector, let's just make another combination. We have an actual vector. Let's take a polar vector. So polar vector dotted with an actual vector. How would this transform, you think? What would we get? In a prime coordinate system versus what will come here, right? And you can tell me verbally, you don't have to type anything. What would come here besides the transformation vector? And then you have the polar vector times the dot product of the actual vector. Right, so these are the normal coordinate system. M, of course, transforms it, right? You will have actually M squared, right? Or I should rather write M, right? Because each one of these will have to be transformed, right? And what would you get here eventually? Is it odd powers of determinant M or even powers of determinant M? Let's call it. Let's simplify the question.
I think it's odd powers.
Odd power, I heard odd power. It should be just one, right? Because
Yes.
only this guy, when you transform it, so the actual vector looks like the determinant M, one of the M's, and the actual vector in the unprimed coordinate system. And the polar vector transformed just like the M and the polar vector. So you only have odd power. So if you have actual character appearing once on the side and on the left hand side, then it will have only one determinant factor there. That means this is not a scalar. It is what we call a pseudo scalar. There's an extra determinant M factor, which is plus minus M appearing in there. So a dot product always will not be the same as the dot product in the unprimed coordinate system. It may have a factor of minus M coming in. So you need to be very careful when you are looking at when you're mixing up different physical quantities that involve polar vectors or actual vectors or the vector triple product of things. When would you encounter this quantity like 4? Whenever you have a vector, let's say, when you have a vector dotted with another vector U crossed with the W. This is going to be a pseudo scalar. Okay. What did I write here? That's one example of a pseudo scalar which would transform differently from an ordinary scalar. Okay, so let's take a look at now what's time, 8:45. I think this is a good time. So let's do the quiz first. I'll give you 10 minutes for it. So we will stop at 8:55. And here is your quiz question. It's very simple, not too complicated. Take a new sheet of paper start writing on it. So you can take a picture of it and then upload it on Western Online in the quiz 2 Dropbox in the assessments assignment section. So I will create the Dropbox right now. Okay, you have about 2 minutes, so I'm hoping you're done. Okay, we're going to stop right here. So stop your work on the quiz. If you need a few minutes, you can submit it right after the class by taking the picture and stuff. So let's now move on to the next topic, which is the Helmholtz theorem, which is crucial for what we are doing in E&M. Is the question that you can ask is, what do I need to know to determine a vector field completely in a given region of space, right? That's what the question that we are trying to answer in electricity and magnetism. And of course, there are sources for both the electric and magnetic field. There is a reason why these fields get created. So without worrying about the sources for now, what's the mathematical minimum that you need to be able to determine a vector field? That's the question, right? So let's say we have a completely arbitrary vector field C as a function of R that we are trying to determine at all points in space. We could think about, and this is what Helmholtz did, the same Helmholtz that made these Helmholtz coils, which are two sets of coils with the current going in either the same direction or the opposite direction. I believe it is the opposite direction current that allows you to create a magnetic field at the center along the axes of these two coils. At the center between the two coils, the magnetic field can be created to completely cancel the Earth's magnetic field. And so Helmholtz coils have a very, very practical importance. If you want to study the effect of magnetic field on certain atomic or molecular properties, first you have to create a region of space in which there is no Earth's magnetic field. You want to completely cancel out Earth's magnetic field, and the Helmholtz coils allow you to do that. Most of the atomic physics lab, you will see that Helmholtz coil is the first important sort of experimental element that is necessary, because you can manipulate the magnetic field. And then, of course, along with canceling the magnetic field of Earth, you can create a known magnetic field of a constant, almost constant at the center, and it's horizontal. It's actually along the axis of the coils. So you can actually move the coils, orient them in whichever way you want, and you can create a magnetic field of a given magnitude and of a known direction. Okay, but that's just Helmholtz's other work. One of his mathematical work is here, which is, and in the old times, same thing goes with Maxwell, Faraday. they were not just doing physics, one aspect of physics like we do these days, like I am a theorist, Dr. Babu, Dr. Malur, they are experimentalists, Dr. Araja, he's an observational astronomer. There are a variety of, and then Dr. Rapchak used to do computational physics. So there are a variety of different directions of inquiry in physics now. You hardly will find a person who is expert in multiple different directions of inquiry. In theory, you kind of do theory and computational together, but otherwise, it's only mostly one side of things. But that was not the case in the 18th and 19th century. Everything was physics, and they would do all different interesting things. Yeah, that's just a side remark. So what we need is we are going to just ansatz, right, assumption that we can split the vector field that we are trying to determine into two components, C perpendicular and C parallel. That's what these subscripts are to be read as, perpendicular and parallel, where the perpendicular component, the divergence is 0, and for the parallel component, the curl is 0. Right? So that's just the restriction on how we split. Okay. So then the question is, can we determine C completely, fully, if we know its curl and its divergence? Right? So we know the divergence, right? If there is some other external mechanism that allows us to determine the divergence and curl of that vector field, is that enough to determine the full vector field? Okay, so that's the question that we are asking, or Helmholtz asked, and the answer turns out to be unique. And in your textbook, there is a proof, I think 1 or 1.5 page long proof of the Helmholtz theorem. We're not going to go into the detail. It is a reading assignment for you. So let me add the reading assignment here, and then I will got the spelling wrong. Okay, proof of okay, so that's your reading assignment. Make sure you are completing all the reading assignments. If you don't do it, you will find yourself struggling on the exam. So because this material you're expected to know in the exam. So what we do is, the ansatz again is that there are two other fields. One of them is a vector field, and the other one is a scalar field. So this is a vector field. Omega is a scalar field. And you could take the curl of F and gradient of omega with a minus sign in between, and that gives you the complete vector field back. Okay, so that's the idea. But of course, we don't know F and omega, right? So where are we going to get that? All that we know is the divergence of C. Okay, so we know the divergence and we know the curl. Is that sufficient to determine C? And it turns out, yes, it is. This is the statement of Helmholtz theorem, right? So this is the Helmholtz theorem, which says that the C will be given by curl of F minus gradient of omega, where F and omega are defined like this. F can be determined at all points in space if we know the curl of C, the curl of the vector field at all points in space. And if we know the divergence, then you can determine the scalar field, because divergence is scalar. It's only going to give you the scalar field. And of course, you have these r minus r prime and the q bar integrals, which is integral over space of over all space, where the divergence C of C and curl of C. Okay, so it may seem a little roundabout, but that's kind of how it is. You have integrals as well as the derivatives appearing there. We are not going to prove it now, but you can take a look at it. That happens to be extremely important in determining any vector field if you know its divergence and curl. And you know from the Maxwell's relations, we have a mechanism for finding the divergence and curl of a vector field, even if we don't have a mechanism directly to find the vector field itself, right? So that's where this utility of Helmholtz theorem comes in. Maxwell's relation give you the divergence and the curl, and then you can plug that back into this Helmholtz theorem relation to determine the whole vector field in all of space. Okay, everybody with me so far? Make sense? Okay, so the idea is that the solution is unique, right? That's the crucial part. The solution is unique. That means if you found by some hook or crook, and there are quite clever tricks that exist in determining electric and magnetic fields, which we will take a look at one of them. Some of you may have heard, or I think almost all of you have heard, the method of images technique. It is possible because of this uniqueness of the Helmholtz theorem. If you found the solution by some means, then that solution is unique. It's guaranteed to be the only solution for that problem. And that's the power of it. And this uniqueness is, to understand that uniqueness, you need to look at the proof, which I'm skipping here. So we're going to now take a look at electrostatics. We have about 10 minutes. So we will take a look at some of the initial set of concepts from E&M. And now we begin essentially chapter 2 from the book. There are a couple of other mathematical topics still there in chapter 1, which we're not discussing because we won't have any need for them, at least in this class. All right, so you, of course, before we start with Maxwell's equations, let's start with the Lorentz force. If you put a charge particle in, with a magnitude of q, let's say it is inside the electric field E, and it has a velocity in the direction, or the velocity vector is given by v, then v cross b gives you the velocity there. Okay. So, do you see any issues with this expression? Do you think everything is okay? Just by looking at it, I'm not asking you from your memory if it is correct or not. I'm asking you within the context of what we learned today, right? So this is the electric field. And that's the magnetic field. Okay, so what can you say about the vector character of these? Q and E, is the electric field, so it's an ordinary vector. So this part here, the first term is a polar vector. If you're adding another quantity to it, that needs to be a polar vector as well. Are you convinced that it's a polar vector? There is a cross product coming in. Why we have V cross B? Why not V cross E, right? Why the electric field, the electric force does not depend on the cross product? Why only the magnetic one depends on the cross product, right? That's kind of the question. So V, of course, is an ordinary vector, right? We know velocity is a polar vector. And let's assume for now that B is a polar vector also. Okay, I'm saying assume because then, and so then P cross B would be an axial vector. and that would be problematic. You cannot add an actual vector to a polar vector. That's going to lead to physically, not a very meaningful quantity. You cannot do that. That's not allowed. That means this has to be a polar vector. And that means this here, the V cross B, sorry, has to be a polar vector. If that has to be a polar vector, and because V is a polar vector, you're taking a cross product of a polar vector with some vector, and you expect the output to be a polar vector, then this cannot be a polar vector. B has to be an actual vector. Okay, so remember, magnetic field transforms differently. You need to be very careful, right? So if E and B were sort of fundamental quantities, then it would be really weird to understand why electric field E is a polar vector and why B happens to be actual vector. So it turns out these field pictures are useful. They are useful mathematical tools, but you need to be careful with them. They are not the fundamental. You are not going to be directly measuring electric field or magnetic field in any experiment. They're not fundamental in that sense. You can only measure them with respect to their effect on the charged particles. So the physical quantity that you always measure is the force. And then you use some of these relations that we have found to transform them and then determine the electric and magnetic field. Does that make sense? Everybody with me? So if you think about what is more fundamental, it's not the electric and magnetic field. Mathematically, yes, that's a mathematically very, very useful tool. That's what the field concept allows you to do. But when it comes to actually measuring things, it is the forces that you measure. So if you want to sense the electric field in a certain region, you need a test charge. And on that test charge, you find what is the force acting on that test charge in that region. And that gives you an idea of what the fields must be, right? And this, of course, determining the Lorentz force is a very, very important element of all of the particle physics experiments, right? That's how we determine what sort of particles we have found in a particle accelerator, right? So B is an actual vector. And an actual vector cannot come on its own. It cannot be a fundamental quantity. It has to come from something else, from some sort of a cross product. That means there's some other quantity that is more fundamental, which is then the potentials, right? So the electric and magnetic field themselves are not, let me actually write down, turns out to be, let's see, dl crossed with, and then R, of course, is down here, crossed with A. Okay, so the vector potential A of R cross product with DL, both the vector potential and the DL are now polar vectors. They're more fundamental. Then you add the cross product between them, and that's what allows you to find the magnetic field, right? So, and then there's, of course, let's say J, and then you do D cube R. Okay.
Dr. Kapale, excuse me.
Yeah. Yeah, go ahead.
You said the magnetic field B is the axial vector, right?
Right.
So is it always an axial vector or?
Always an axial vector, right? That's
Yes.
the vector character of B. It will always be an axial vector because it's
So
not
the axial vector is always an axial vector, and the polar vector always polar
will
vector.
always be a polar vector, right? So
I
like the velocity, for example, velocity is a polar vector. It would transform accordingly. B, because it arises from a cross product, it always is arising from a cross product between J, JDL, right? J is the current density, right? So, right. So let's say you have a region of space where there is some current density here, and so let's take a small line element along that direction called DL. The current that's going to pass through is going to be J of R DL, and that's at position R, let's say, and you're trying to find, And then you want, I think to be clear, I need to be more specific here. I should do R prime for the integration vector, and R prime also there, R minus R prime squared. So I'm trying to find, let's say, B of R at this point in space, but I need to take into account that the current that is causing the magnetic field is at a position R prime, right? And so this vector, the distance between the source point and the magnetic field is what matters. So this is the R minus R prime vector, okay? And that's what is important. That's the distance that matters, not the actual amplitudes of the R and R prime, right? So the main important point here is this cross product. If somebody gave you a source for the magnetic field, which is the current density, always is, it's always the cross product that leads you to the magnetic vector. And so that's going to be actual vector. That also, just kind of tells you that electric and magnetic fields themselves are not fundamental. You can't do a single measurement of them and arrive at the answer. You have to rely on certain other physical measurement. What you measure is actually forces. Okay, so that's that. In electrostatics, because the name says statics, what we are going to do is remove the time dependence. So electric fields are only going to be functions of the position, and magnetic fields are also going to be just the functions of the position, no time dependence. Right? Time dependence will come when you start talking about electromagnetic waves and how they change. Remember, the charge E is quantized. But as we already talked about the discussion of the simplifications in electrostatics, we are going to assume that it is continuous, right? The charge distribution that we encounter are always going to be continuous. And so we are going to have, let's say, a total charge in certain volume of space is going to be a charge density and an integral of that. And we are going to assume that it is a continuous quantity. This is a volume charge density. It doesn't have to be that, it can be a surface charge. So you would then have a dA sigma R. So that would be a surface charge density. You can have a linear charge density. Then you would just have a line integral. Let's call it lambda of R. That's a linear. Actually, it should be lambda of L then, because L is now our quantity. The length coordinate rather. And so you can write those kinds of things down. How do you get, so I'm just going to take a minute here. How do you get the charge density connection with the other parts of the physics? Like, for example, quantum mechanics. It comes from d cube R2, d cube R3, and so on, d cube Rn, and your quantum mechanical wave function psi, which is a coordinate of R1, R2, R3, and so on up to Rn, and mod square of that. So it's the Q times the psi mod square that gives you the total charge density. And we are assuming, of course, these are the coordinates of the n indistinguishable particles. With charge Q. So if you have multiple charges in your system, you use the wave function. And in some sense, that is sort of leading to this, the continuous assumption, wave function modulus squared multiplied by Q integrated over all the coordinates. That's what gives you the charge density rho of R at any point R. Okay, everybody with me so far? Okay, so that's quantum mechanics. If you ever want to connect that, if you're looking deeper into the details of where these charges are coming from, or you have a very macroscopic sample, you're looking at it in more detail, like in condensed matter physics, for example, you would be determining this psi using some computational technique, and then you would determine rho of r, and then that would give you connection of the microscopic quantum mechanics with the macroscopic electrostatics and magnetostatics. Same thing applies for current densities as well. Okay, so that's a good point to stop.